Oh. All right, ladies and gentlemen. So we finished talking about vectors, and why do we do vectors? Vectors are a tool. Vectors are a tool. They allow us to express motion of things in multiple dimensions. Now, the rest of the unit is about projectiles, and projectiles is really the meat and potatoes of what we're doing. I've got kind of an interesting toy here. It's a cart. It rolls along. It weighs a lot, so it has lots of inertia. But for some reason, one of the wheels is a little janky in that it wants to curve a little bit. So it wants to curve that way a little bit. Hopefully it's not going to matter for the purposes of our experiment. Let's pretend that you're in the back of a truck, and because you're young and stupid, you're in the back of the truck, not wearing a seatbelt, and you've got a bowling ball, and you're cruising down the road. You've got a bowling ball in your lap, you're cruising down the road, and you throw the bowling ball into the air.
Why? Why do you like this?
As your neighbor's cruising down the road. Does the bowling ball end up behind the car, behind the truck, in front of the truck, or right back in your lap? Yeah. So let's just test this. So what I've got here is I've got a thing with a little spring in it, and I've got a pin, and I got a little steel ball, and I put a pin in the spring. So when I pull the pin, up comes the ball. Okay?
There it is.
Yep, there it goes. So I got a pin, and I pull the pin, and up comes the ball. Make sense?
Yes.
All right. So this is what we're going to do. I'm going to try to do the same thing like I'm doing here, but I'm going to do it when the cart is moving. Okay. So if you think the ball is going to go, as this thing is going to roll, I'm going to pull the pin. Clink. Okay. So if you think the ball is going to roll or fire and end up in front of the car, raise your hand. Okay. If you think it's going to go and end up behind the car, raise your hand. Okay. And if you think it's going to go right back in the cup, raise your hand. Okay. So looks like about 0, 4, and 24. Okay, let's check this out. I'm going to put my finger right here, and hopefully it will work. Hopefully I'll be able to catch it.
It worked.
It worked. It went right back in the cup. Okay, now I got it. Here we go. What the heck? Why? Well, what the heck? Why? Doing it again. Okay. It did go in the cup, yeah.
It landed next to the
It's because the cart, for some reason, this cart's probably 30 years old. The cart is actually starting to curve away. But, okay, so what the heck, why? Well, when this thing's cruising along, it has velocity in what we're call the x direction. Okay? And the ball goes up, and the ball is, at the moment it leaves the spring, is being acted on by what? Gravity. And gravity says, oh, I didn't realize you were moving horizontally. By all means, keep going. Because gravity only acts in only acts in what direction? The vertical direction. Gravity has no idea what's going on in the horizontal direction. All gravity sees is this. That's it. Okay. So the ball and the cart both have the same horizontal velocity. Gravity doesn't act in the horizontal direction. All gravity sees is this. Ball goes up, ball comes back down. So the ball has the same horizontal velocity that the cart has, because gravity acts only in the vertical direction. That principle is really important. Motion in the vertical direction and motion in the horizontal direction are independent of each other. That is critical, you understand this. When we're talking about projectiles or any motion, motion in the horizontal direction and motion that is perpendicular to that in the vertical direction are independent of each other. One doesn't know what the other one's doing. Do you know what year Alaska became a state?
1956.
Pretty close, 1959. I have two identical Alaska quarters, minted in 2008. There's a bear on them in 1959. And what I'm going to do is I'm going to put them over here in this little jig that my mentor taught me how to make. And what's going to happen is I'm going to pull this thing back. So I got one in front, one in back. I'm going to pull this thing back and I'm going to let it go. And when I let it go, 1/4 is going to fall, 1/4 is going to launch up. Okay. 1/4 is going to fall, 1/4 is going to launch up. My question to you is, should I hear clink clink, or should I hear clink?
Clink.
Okay. If you think I'm going to hear clink clink, raise your hand. 1. If you think because I'm going to screw up, right? If you think you're going to hear a clink, raise your hand. All right, so let's find out. Oh, I'm going to put it Washington side up, bear side down.
Your side.
Clink. Yeah, we heard clink because as far as gravity was concerned, what were the quarters doing? Yeah, they were both falling. All gravity saw was clink, 2 quarters falling. Now we know that one of the quarters also got some horizontal velocity because a little jig hit it and it went this way, but the other one just fell. As far as gravity is concerned, this happened. Make sense? If that makes sense, okay, question.
No, a question. I was saying.
Okay.
Same thing applies to bullets.
Absolutely.
Yeah.
And this is where actually, great segue. Okay, so Oliver gave me a great segue. If you had a rifle and it was 1 meter up and it was perfectly aligned with the horizon, perfectly horizontal, and you fired the gun, nothing in the way. It's like you went out to like the Mojave Desert, you can just see all the way to the end, nothing in the way. You fired the bullet. How long would it take the bullet to hit the ground? 10 seconds? Okay, 1 meter up. We're gonna set it at 1 meter. We're gonna set the gun at 1 meter, perfectly horizontal. We're gonna pull the trigger. 0.1, 10, 0.2. I'll tell you how long it'll take. Everybody got your mental stopwatch? Here we are.
Take as long as it takes to fall in.
That long. That's how long it would take. What? Okay. This is a yardstick, not a meter stick. So a meter's right about here. Ready, set, go. That's how long it would take. It would fall that fast. Because as far as gravity is concerned, what's the bullet doing? Falling. But it's going really fast. I don't care. We don't care how fast it's going. And neither does gravity. Gravity doesn't care how fast something's going. It only sees in the vertical direction. Okay? That is the meat and potatoes of projectiles. So when we're talking about projectiles, we're talking about things that usually move in the path of a parabola. Okay? And when we evaluate projectiles, we evaluate them in their x motion and their y motion independently. Okay? And here's the crazy thing. As long as we ignore air resistance, the horizontal velocity is what? If we ignore air resistance, the horizontal velocity of projectile is what? Constant. Yeah, it's constant. So if I throw this ball, we know that gravity is going to grab onto it and pull it down. Couldn't have planned that better. So we know that gravity is going to pull it down, but as far as horizontal motion is concerned, there's nothing to push back. As long as we ignore air resistance, and we're going to ignore air resistance, there's nothing to push back on the ball. So it has a constant horizontal velocity. The vertical velocity is getting slower and slower and slower, coming to 0, and then faster and faster and faster until it hits a bucket full of computer mice. Wow.
Are you going to pick that up? Are they though?
I'll pick it up. Yeah. It's where you're like, it's a mess. Can you pick up the mess? I'll pick it up. Okay, so if you diagram projectile motion, what you have is horizontal motion that is constant, vertical motion that keeps speeding up as though it was in free fall, and that makes a fun little parabola. Parabola. Makes a fun little parabola. Depending on what syllable you put the emphasis. So, vertical motion is simple free fall, where acceleration is negative 10 meters per second squared, and velocity is acceleration times time. and horizontal motion is constant. There's no horizontal acceleration. That means horizontal velocity has to be constant. So that's what makes a parabola. Now, this is if it's launched horizontally, like off a cliff, or a meter off over the Sahara Desert, or the Mojave Desert. But if you do a ground-launched projectile, you're basically doing the same thing backwards. You're doing this part of the parabola, and then the same parabola back down. A ground-launched projectile makes a parabola as long as we ignore air resistance. And like I said, in this class, we ignore air resistance. It is the realm of differential equations in calculus where we don't ignore air resistance. So if you don't want to ignore air resistance, you're welcome to take third-year physics in college once you have differential equations. Or use a computer. Okay, questions? Moving on. Okay, so projectiles, this is a stroboscope of basically what I've replicated with my little wooden jig. This is a red ball and a yellow ball, and then flash, 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 flash onto film. It's pretty classic. This is a very classic picture. You see it all over the web. Basically, the red ball is dropped while the yellow ball is launched, and you can see that they're in the same places vertically, and horizontally, the yellow ball continues on. Okay. So let's draw some vectors on this diagram. I guess I should probably use green. What would the horizontal motion vectors look like on the yellow ball? At every point in time, what would their motion look like? If we were to draw vectors representing their horizontal velocity, what would it look like? It'd be that way, and how would their length, what would their length look like at every point? Exactly the same, yeah. If we were to draw the velocity vectors, they would have exactly the same horizontal velocity constantly. Okay? They have the same length at every point in time because there is no horizontal acceleration. And without a horizontal acceleration, you have to have a horizontal constant velocity. What would the vertical vectors look like of the yellow ball? Down, and how would they change? They get bigger. Okay, so you start with nothing, tiny, a little bit bigger, 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 and a little bit bigger. Okay. So that's what the vectors would look like in the vertical direction. Would the red ball have any horizontal vectors? No. How does vertical vectors look? Same as the yellow ball, exactly. I don't know if that's going to happen or not. We're going to find out. So I'm just going to freehand it and see what happens. Maybe I'll get lucky and it'll be the right size. How'd I do?
Not too bad.
Cool, thanks. Okay, so that's what the velocity vectors would look like. Vertical motion would be simple free fall given by d equals 1/2 at squared, or v naught t plus 1/2 at squared. Horizontal motion is constant velocity. What distance formula do we use when we have a constant velocity? D equals vt. Okay. And now I'm going to add something. I'm going to add that to the velocity. We're going to start slapping subscripts on velocity to say this is vertical velocity or horizontal velocity. And we can make this AY if we want, or G. So we're going to say dx equals vxt. Distance in the x direction equals velocity in the x direction multiplied by time. Okay. How are we doing with this stuff? Give me a thumbs up if you feel good about this. Okay. Any questions? In that case, let's move on. Oh, I love this one. I'll just give you a second to watch the animation here. It's like, bam! You can do this at Walmart. See, it's at Walmart. They have this. You can do this at Walmart. So, extra credit, make a video, replicate it.
No, I'll be the one. I'll be the ball. I need the balls. She just comes over and smacks me.
Okay, ground launch projectiles. You don't need to write anything down of this unless you want to, because everything that we have here is kind of, it's up to you. So suppose we fire an artillery shell with a velocity vi. Now, if it's given the subscript I, it's initial velocity, and it doesn't mean horizontal or vertical, it means both. So if something goes out vi at an angle of theta, we can do some math. Okay? We're going to do some math here in a second. Okay? We can figure out the final velocity, the flight time, the maximum range, the maximum height, because whatever goes up comes down, right?
Yes.
So this is what we're going to do. I'm going to turn the light on, and I think I'll do it over there. And I need you to give me a velocity and an angle. It'll be very similar to our potato launching. So here's our baseline, a cannon, a wheel on the cannon, barrel, projectile. Whoosh. Okay. So boom. All right. So how fast is the projectile leaving? Oh, sorry, America. Sorry, Angelina. Okay. How fast is the projectile leaving the barrel? What's the VI?
20.
20. VI is 20 meters per second. And at what angle is the potato or the projectile leaving the barrel? 60, 62 degrees. Okay, 62 degrees. So between that and the horizontal is 62 degrees. Then we just take it apart. Now, here's the thing. The VI by itself is not useful to us because it is motion in both the vertical and the horizontal direction. So we have to resolve the velocity vector into its components using that formula that we used a whole bunch last week. So the first thing we need to do is resolve the VI into Vx and Vy. So do that now. Bang on your calculator, find out what the Vx and the Vy are when the projectile is 20 meters per second leaving at 62 degrees. I'm going to leave, not leaving my quarters out because I'll lose them, but I'm going to leave this out if you guys want to play with this. Here's the pin right here. I'm going to leave that out for you. It sounds like from some crossed arms that you actually have your Vx. So I'm going to draw this as two vectors as with the Vx and Vy. Vy and Vx. So I'm going to draw it as two legs, as two vectors, x and y. So what is Vx? Anyone? 9.4? 9.4 meters per second. So Vy is 9.4 meters per second. Right. separate T top from T total. So T top is going to be the time up here, T top, and T total is going to be the time down here. So the projectile is going to go, boo! Okay, now T top is right there. Okay, so what's the time it takes to get to the highest point? Yeah, 1.77 seconds. T top is just Vy divided by our friend G. The time to get to the top is just Vy divided by our best friend G. .77 seconds. Cool. You want to check off one of these four? Flight time. Yeah. So flight time is just going to be T total. T total is just going to be T top times 2. So if it takes 1.7 seconds to go up, it's going to take 1.7 seconds to come down. So the total flight time is what? 3.54? Sounds good to me. 3.54 seconds. Hold on there, buyers. How do I know it's 3.54 seconds? Because 1.7 seconds going up, 1.77 seconds coming down. What goes up comes down. First it has to unfall, then it has to fall. And the time it takes to unfall and fall must be the same. Lane.
What happens if it goes so fast that it starts orbiting netly around the Earth?
If it goes 8,000 kilometers per second, or 8,000 meters per second,